Hello everyone, welcome to CST 351 Lesson 3, AI Problem Solving by Search. In this lesson, we will cover the following. Last week, we talked about intelligent agents, those digital brains that perceive and act. But how does an agent, say a GPS or a game AI, figure out the best next move? It doesn't guess, it searches. So in this lesson, we are going to break down exactly how we, as computer scientists, formalize a real-world problem like navigating a maze or solving a puzzle so a machine can actually solve it. This is where the magic begins. So let's get started. Now, take a look at this image. It looks like a complex network, right? Now, this is essentially what a complicated problem looks like to an AI, a maze of possibilities. The bright red line is the solution path, the optimal sequence of actions we want the agent to find. So now recap that an intelligent agent from week 2 simply perceives and acts to maximize its performance. Now, what happens when the best action isn't obvious? Like driving from Lagos to Abuja, there are dozens of routes. Now, the agent can't just guess the fastest one. In classical AI, the whole process of figuring out that sequence of moves is called a search problem. The agent systematically explores possibilities to find a path to its goal. So when we say search, think intelligent planning. Before an AI can solve anything, we have to give it a map and a rule book. We formalize the problem using 6 key components. Think of them as the 6 pillars of a solvable problem. The first state is the initial state, and it's simple. Where it answers the question, where does the agent start? For our Lagos to Abuja trip, for example, so this is your current GPS location. So the initial state is your current GPS location. Then we have the actions and operators. These are the legal moves. You can turn left, turn right, or go straight. We have the transition model. This defines the result of taking an action. If I'm in Awolowo Road and I take the turn right, I take the turn right action, where do I end up? So the model tells the agent the resulting state. Then we have the goal test. This is the finish line, a function that checks if the agent is currently in the goal state. For our trip, the test passes when you reach Abuja. Okay. Then we have the path cost. This is crucial. It's the numerical value we assign to a path. If your goal is the fastest route, the path cost is time. If your goal is the cheapest route, the cost is fuel and tolls. Okay, so lastly we have the state space. This is the complete map, the graph of all possible reachable locations and all the connections between them. So once you define these 6 things, you've translated a real-world problem into a language the AI can understand. Now let's look at the state space versus the search tree. We have to distinguish between 2 terms that confuse many beginners: state space and search tree. The state space, which is the graph. Now look at the graph on the left. This is the full map of the problem, all unique states and all possible legal transitions. It represents the entire environment. It's a graph, so paths can look back on themselves. We call these cycles. Now for the search tree, look at the tree on the right, starting at the root. This is the explored path. It's generated by the search algorithm itself. Every node in the tree represents a path taken from the start. So a single state from the graph can appear in many places on the tree if the agent explores it multiple times or via different routes. Now, the key takeaway is that the state space is fixed. The search tree is dynamic, is the algorithm's history of exploration. So now let's take a look at a practical problem formulation example. Let's put those 6 pillars into practice using a classic AI puzzle, the 8 puzzle. This is a simple sliding type puzzle where you rearrange 8 number tiles and 1 blank space to match a goal configuration. Now the component is 8 puzzle definition. The initial state is any configuration of the 8 tiles and the blank space. Now the state space is the all 181,440 possible configurations. The actions is moving the blank tile left, right, up, or down, whenever or wherever is legal. Then the path course is the number of steps, the number of moves that will be taken to reach the final state. Now, if you can define these for any problem, whether it's planning robot movement or designing a circuit, you are ready to start programming the search algorithm. Not all problems are the same. The type of search technique we use depends heavily on what the agent knows about its environment. We classify problems based on 2 main factors: observability and determinism. For single-state problems, these are the easiest. The environment is deterministic, that is, actions always work as expected, and fully observable, that is, the agent always knows its exact location. Example is route finding on a reliable, fully mapped road. For multiple state problems, the environment is partially observable. The agent doesn't know its exact state, only a set of possibilities, that is a belief state. For contingency problems, the environment is non-deterministic, that is, it is stochastic. Actions might fail or have multiple outcomes. A robot acting on slippery terrain is an example. The solution must be a contingent plan that plans for failures. For exploration problems, imagine the agent is in a completely new environment, a new cave or an uncharted part of the internet. The state space is unknown. So the agent's goal isn't just to find the path, but to discover the environment itself so it can eventually find the goal. For adversarial problems, this involves another intelligent agent trying to defeat you. Think chess or checkers. We'll tackle this later on the course. Now here is the biggest enemy in classical AI: combinatorial explosion. The core concept entails that the size of the search space grows exponentially with the complexity of the problem. For the formula, the number of nodes an algorithm might have to explore is roughly big O of B to the power D, where B is the branching factor, that is the average number of actions from any state, and D is the solution depth, that is how many steps it takes to reach the goal. So for example, imagine an agent with only 10 options at every step, that is B equals 10, and the goal is 20 steps away, that is D equals 20. The number of nodes is 10 raised to power 20. That's a ridiculously huge number. Now, the reality is simple. Exhaustive brute force search is computationally impossible for most real-world AI problems. We simply do not have the time or memory. Now, because the problem is so vast, our first attempts at search are what we call uninformed or blind search. Now, the limitation is that these algorithms use only the 6 formal components we defined. They have no domain-specific knowledge to estimate whether one path is better than another, so they search blindly. They simply follow a mechanical procedure. And we are going to quickly look at the two classical uh, blind strategies. The first one is the breadth first search, and the second one is the depth first search. That is the breadth first search, BFS, and the depth first search, DFS. Now, the breadth first search is often referred to as the patient explorer. The strategy um, entails being systematic. BFS is systematic. It expands all nodes at one depth level, that K, before moving to the next level, K plus 1. So it explores uniformly outward from the start. For the mechanism, it uses first in, first out queue, that is FIFO, FIFO, first in, first out queue, to manage the nodes it needs to visit. So think of a line at a bank. The first person in is the first person that will be served. First come, first served. So in simple terms, BFS finds all possible one-step paths, then all two-step paths, then all three-step paths, and so on. This guarantees it finds the shallowest, that is the shortest solution first, if one exists. Next, the aggressive plunger, that is the depth first search, DFS. For the strategy, DFS is aggressive. It explores a single path as far as possible, plunging deep until it hits a dead end or the goal. If it hits a dead end, it backtracks. So for the mechanism, it's very straightforward. It uses a last in, first out stack, LIFO, or recursion. Think of a stack of plates. The last plate you put is the first one you take off. So a critical caveat, however, is that because it keeps going deeper, if the search space has an infinite path, TFS can get stuck and never find the solution, even if one exists nearby. We often need to set a maximum depth to prevent this. For, for performance evaluation and trade-offs, we access the algorithms on four critical criteria: completeness, optimality, time complexity, and space complexity, that is memory. So for completeness, BFS is complete. It always finds a solution if one exists, because it searches level by level and will eventually reach the goal depth. TFS is not complete in general. It can get stuck going down an infinite path and may never return to explore branches where the solution exists. For optimality, BFS is optimal when all steps costs are equal because it finds the shallowest solution. TFS is not optimal because the first solution it finds may be long or inefficient. For time complexity, BFS requires exploring almost every node up to depth D. So the complexity for BFX is about big O of B to D, to the power D, which is very large. DFS, worst case, explores all nodes up to maximum depth M. So complexity is about big O of B to raise to M. Now for space complexity, BFS needs to store all nodes at each depth, which is extremely high memory. That is big O of B raised to D. DFS on the other hand only stores current path, very low memory, which is big O of B multiplied by M, that is BM. So the summary of the trade-off is that BFS gives better guarantee that it is complete and optimal, but consumes huge amounts of memory. DFS, on the other hand, uses tiny memory, but it's not guaranteed to find a solution and does not give optimal ones. So, all right, let's wrap things up. Today, we explored the foundation of classical AI problem solving, which is search. We learned that before an agent can solve any problem, it must first formulate it clearly using 6 components: the initial state, actions, transition model, goal test, path cost, and the full state space. We also saw that search spaces grow ridiculously fast, and this exponential growth, what we call combinatorial explosion, is the number one reason search AI becomes difficult in real life. Then we compared the two basic uninformed search strategies, which is BFS and DFS. BFS gives strong guarantees but eats memory like crazy. DFS uses very small memory but can get lost on deep or infinite paths. So both methods have limits. The big message is this: blind search alone cannot handle large real world problems. We need something smarter. So next week we take a major step forward into the world of informed search. This is where AI stops searching blindly and starts using heuristics, that is, intelligent guesses, to guide the search toward the goal much faster. These heuristics act like a torchlight in a dark maze, helping the agent avoid dead ends and focus on promising paths. We'll look at what heuristics are and why they matter. Read the best first search, A-star search, which is the most famous and powerful search algorithm in classical AI, and how these methods avoid the explosion we saw today. This is where search becomes truly practical and where AI starts to feel smart. So great job, and see you next week by God's grace.